So this is the third and last lecture for this week's topic of flows in networks. As I explained at the start, we're concentrating on this topic this week. It's quite deep mathematically, and yet I want to finish it this week so that next week we can go on and talk about binary codes, which is a completely new departure. Now, the lectures for the remainder of this semester will actually be in this sort of format. I've exhausted the recordings from last year because, in fact, the last time I lectured in the Lucas Theatre was when I talked about Kruskal's algorithm, which you saw a bit of last week, I hope. I actually travelled to Italy the day after that, but because the situation in Italy deteriorated so dramatically, I found myself back in London two or 3 days later, just before Italy went into national lockdown. And I myself haven't been to campus since then. Anyway, let's get back to networks. And I want to remind you that we're given a network. So what does that mean? It means we have a set of vertices, sometimes called nodes. We want to apply this labeling algorithm, so for that purpose it's a good idea to order the vertices. Normally in these examples we use alphabetical letters, letters of the alphabet, A, B, C, D and so on. So although you put the source first, the source is called S, after that you should start from A, B, C in that order, because when you want to add vertices you want to take them in some order. It doesn't really matter, but you need to make a choice. And remember that if we just start with the network itself, we may or may not have a flow on it, but the crucial thing is that each arc or each directed edge has a capacity. So that capacity has to be a positive number. If I write C of UV, it's like the weight. Previously we called weights D of UV, now we're calling them C of UV, where C stands for capacity. And if I write C of UV, I'm actually implying that the arrow on the edge goes from U to V. So as I've explained in both of the previous talks, the idea is to try to get flow. We start with some initial flow which could be zero, but we try and get more flow from the source to the sink. And the method we use is to try and construct what's called an augmenting path. And we do that by essentially doing a breadth first search. But we don't add all the adjacent vertices. We only add adjacent vertices satisfying certain conditions depending on the existing flow. And we do that once. Hopefully we get to the source, we get more flow to the, we get to the sink, we get more flow to the sink, and then we sort of put everything we rub out all the labels and start again and try and do another iteration. We may need several iterations before we actually get a maximum flow. So what happens in these iterations? So the first thing to say is that you do one at a time. You try and get from the source to the sink. Once you've done that, if you've done that, you can then change the flow, update the flow, increase the flow numbers, but then eliminate all your previous labels and start again. Now, during this process, what happens is this. We start with the source, and then we form a queue. Starting from the source, we start adding vertices. So typically it might start S, A, if A is visible, B, C, and so on. Once we get to a certain vertex, we start looking at adjacent vertices. So supposing we've got to some vertex X. So at the front of our queue, let's suppose we have some vertex X at the front of the queue. Then we look at the vertices which are adjacent to X. And by adjacent, I'm not implying that the arrow has to go away from X. It may go away from X or it may come into X. But we look at all the vertices which are adjacent to X. And if we can get flow in some net sense to those vertices, let's call one of them Y, then we label Y. So if we can, what's called CY, we put a label, we associate to, and we do this in a table, we associate to Y a label. Now this label, before when we did Dijkstra, it was just a number. It's a bit more than a number this time. It includes a number, that's the crucial part. It includes this number L of Y, and that tells us how much flow we can get all the way from the source to Y via X. So we've already started from the source and we've done some path to get to X. We can get a certain amount of flow to X, and hopefully we can get some more. If we can get more to Y in some net sense, we label Y. We also remind ourselves that Y came from X, so we add to the label X. We should have really done this for Dijkstra as well, although I didn't bother. When we made a label permanent in Dijkstra, we should have added the vertex that made that permanent. And we also add a sign which corresponds to the direction of the arrow. So if the arrow is going from X to Y, that corresponds to a plus sign. If the arrow is going backwards from Y, that corresponds to a minus sign. Okay, because remember, I've used this symbol to indicate that when you look at adjacent vertices, the edge can go in either direction. Okay, and then if we succeed in getting to the sink, that will mean that we've got some sort of path with arrows going back and forward, some sort of path in the underlying graph that gets us from the source to the sink and enables us to increase the flow from the source to the sink. That's the basic idea. Now I'm going to go through the sort of, if you like, the pseudocode for doing this algorithm, and then we'll see a much more complicated example, more complicated relative to the first lecture, of how you use this algorithm. So you might not follow again all the details on this slide, but you can do the example, follow the example, and then go back and look at these details. So there's a slightly, I think, more user-friendly version than the box in the lecture notes, which is sort of written in slightly more formal language, but essentially it's the same. It's the same text as you'll find in the lecture notes. So I'll just go through the steps, and I'm sort of repeating some of what I've just said. So we start the queue at the source. And in order to apply some sort of formula, it's best to label the source. I'll do this in a table and you'll see this later, but the source gets labelled infinity. So in a sense, that's indicating we can't get any more flow from the source itself. So we're starting from the source. Now, we start with the source. So the first step, the source will be X. X will be the source. And we'll be looking at vertices adjacent to the source. And because S is the source, all the arrows go from the source to the adjacent vertex. So we're only in this first situation if we start with the source. But to do this general step, I'm going to suppose we've done a few vertices and we've arrived at some vertex X. As I said before, so we're starting from the source, and we've already added some vertex to a queue. We've come to a vertex X. And now we're looking for vertices which are adjacent to X. That's what this is saying. So let's suppose that Y is adjacent to X. And in the first part of the algorithm, with this if here, we're supposing that the directed edge, the arrow goes from X to Y. If that is the case, how can we get flow from X to Y? We need spare capacity. So assuming that we have spare capacity, that means the edge is not saturated, we do CY, so we add Y to the queue. So there'll be some queue here, which I sort of write, maybe we start by adding A and B to the queue, and eventually we get up to X. And we choose the vertices adjacent to X in some alphabetical order, typically. And if the first of them is Y, which might be, well, it's possible, then we would add, in this situation, Y to the queue. So we add Y to the queue, capital Q stands for Q. And we label Y. And what do we label Y with? Well, we want to say how much flow we can get from S all the way to Y. Now we know how much flow we can get to X. That's L of X. Okay, that's L of X. So can we get all that flow to Y? Well, we can if we've got enough capacity. If we don't have enough capacity to get all that extra flow to Y, we're limited by the capacity, by the spare capacity of the pipe from X to Y. So it's going to be the minimum of L of X and this spare capacity. We can't get more flow to Y, even if this capacity here is 100, say, we can't use that unless we've already got 100 to X. So that's the formula, or the sort of labeling formula, not dissimilar to what we saw in Dijkstra's algorithm, the labeling formula. And then we label Y, we have a table, and underneath Y, as you'll see in a moment, we put these three quantities. We put the L of Y, that's the amount of flow we can get to Y, where it came from, that's X, and in this case plus, I'm going to do minus in a moment, in this case the plus to indicate that the arrow is going from X to Y. Now if it turns out that Y is T, then we essentially stop and we've finished our iteration. Okay, so I'm assuming here, although Y is right at the corner of the slide, I'm assuming maybe we can continue, but if Y is actually the source, sorry, the sink, I mean, is Y the sink? If Y is the sink, then we can actually stop. We've finished our pass, this iteration. Okay, so what happens in that case? So if Y is the sink, then we stop. We don't bother with any more adjacent vertices. And what we're interested in is the amount of flow we have gotten from the source to the sink. And that will just be the label that goes on Y, which is now T. So that's the interesting quantity. It may be 1, it may be 2. In the typical examples, what would be 1, 2, 3, the sort of examples we're doing in this course. So that's what I call epsilon. It's the increment. Epsilon sort of stands for increment. It's the amount of flow we can get in this augmenting path that we're going to construct from the source to the sink. And then that finishes this sort of dynamic part of the algorithm, but then we have to, in preparation for the next step, we have to relabel the flow, because the whole point of this was to get more flow from the source to the sink. So we change the labels, we find the path which we've taken to get from the source to the sink, pushing up the flow each time. And there may be different ways we could have done this, but because of the choices we make, the order in which we put the vertices maybe, there will always be, the algorithm will highlight one particular path which we've used, and we can get that path by tracing back along the source vertices that are recorded in the table, and then we update the flow by adding epsilon if the arrows go forward, as I'll explain, or subtracting epsilon. That I'll explain in the example. I also mentioned it in the first lecture. Along that path, and then we'll have the same network but with more flow from the source to the sink, and we can start the iteration. We can start another iteration. Now, what happens? I've only done the case in which the adjacent vertex had its arrow going from X to Y. What happens if the arrow goes backwards? So we're now in the situation where we have our vertex X at the front of the queue, having got to X from the source, and we now have, we're looking at an adjacent vertex Y, but the arrow goes from Y to X. So what do we do in that case? Do we add Y to the queue? Well, we do add Y to the queue, provided there is non-zero flow coming from Y to X. So we have to ask ourselves, is there non-zero flow on this edge? That's nothing to do with the capacity. The capacity would have to be positive, obviously, which it is. But the question is there non-zero flow from Y to X? If there is, we can reduce it. And reducing the flow from Y to X amounts to increasing the flow to Y in some net sense, because what it means is we've got more flow we can handle at Y to send on further on, probably we've got other vertices, we'll have other edges coming into Y, and we'll have edges going away from Y, because remember, one of our technical conditions was that any vertex had to be on an aligned path from the source to the sink. So in this situation, if we can stop this leakage from Y to X, we've got more flow to go onwards towards the sink. That's the idea. So if we have non-zero flow, what we do is we label Y, again, it depends how much flow we manage to get to X, but the best we can do is increase the net flow to Y by the minimum of this number and the existing flow in this edge going backwards. Okay, so that's the idea, and we therefore label, in this case we add, if that is the case, if there's non-zero flow here, if that number is non-zero, then we label Y with the minimum of these two numbers. And we proceed as before. The only difference is we're now putting a minus sign underneath Y in the table. And then having done what I was telling you both here and here, this is if the edge is going, the arrow is going away from X. This is if the arrow is coming into X. So going away from X, coming into X. Having dealt with X, if you like, we remove X from the queue, or what typically that means is I just put a tick on top of X, and we go to the next vertex in the queue, which will be one of those. Well, no, it might not be adjacent to X. There may be previous vertices in the queue which we haven't used. So as usual, we look at the next vertex, we tick X in the queue. So we'll have our queue, which will typically look SAB, might not have A, we don't know. Maybe the edge from S to A is saturated, so we don't actually see A from the source. But we'll have a queue, it will have X in the queue. What I'm saying is we've now dealt with X, and we may have other vertices in the queue, maybe F, G or something before we added Y. So we dealt with X, and then we now try and deal with the next vertex in the queue, which in this case is F. That's the point. And then we go on, as I say, until the thing stops, and it stops in this situation. Okay, that's the theory. Now let me try and do this example in practice. I don't know if I have time to go to all the details, but here we have an example of a network with a source and a sink. It's usual the source is S, the sink is T. So S comes at the start. We have this table in which we leave a lot of space here because we may need several iterations. We have the source at the front. We list the vertices in alphabetical order, except that T must go at the end, which normally it will anyway. Now, I also like to put the Q at the end of this row, because actually writing the Q is important because we've got to look at the vertices in that order. So let me try and go quickly through these steps, and you can compare it to the theory I've tried to explain. So S is labelled infinity. That's to make the sort of formulae work to begin with. And we look at the vertices which are adjacent to the source. And there are two of them. The arrows have to go away from the source, obviously. They are A and B. So A and B are added to the Q, and because of the alphabet, A is added first. So the Q has now started SAB. And A is labelled, you see, what is the spare capacity? Some people might, I've written the capacities in circles. Some people might write this is 2/4, meaning that we've got a capacity of 4, and we've got a flow of 2. So we have a spare capacity of 2 units, 4 minus 2. So we can get spare flow, extra flow. We can get extra flow of 2 from the source to A. That's what this label is telling us. Similarly, for the vertex B, the existing flow is 5, so again our spare capacity is 2 from the source. 7 minus 5 is 2. That deals with labelling A and B, but we haven't yet used them to scan other vertices. So we've now dealt with S in our queue, and we look at A. A is the next vertex in the queue, so we look at A. Now what can we say about A? Well, there are 2 vertices adjacent to A, neither of which has been visited. We must make sure we only look at vertices which have not already entered the queue. I forget whether I said that before. But anyway, that's important. We never relabel vertices in this setting. So A is adjacent to C and D, so C and D get added to the queue. But the arrows are going different directions. So first of all, we look at C. We have a spare capacity of 2, 5 minus 3, which is exactly the flow we can get to A anyway. So we can label C again with 2, and it's coming from A in a positive sense. On the other hand, when we look at D, we don't care about the capacity being 4. That's irrelevant. We care about the fact that there's some non-zero flow, albeit just 1 unit, from D to A. So we want to cap that off. And 1 is less than 2, so we can cap the 1 unit off. So we can effectively get net flow of plus 1 to A from D. But because it's coming in this from an arrow going backwards into A, we write it with a minus sign. Okay, so we've effectively got 1 unit from D to A. So now what is the next vertex in the queue? The next vertex is B. Now B doesn't see any new vertices because we've already dealt with C and D, sort of circled them. So B, we have nothing to do from B because these vertices have already been labelled. So the next vertex in the queue is C. Now this edge is saturated. Before I put an S, this time I put a cross. This vertex, this edge rather, is saturated. So C does not see E. It can't get. Remember, the condition is that we needed spare capacity if we wanted to label the adjacent vertex. So it can only see F. We do have spare capacity on F. We have a spare capacity of 2, and we've already got a flow of 2 to C, so we can push that flow of 2 to F from C. So F goes in the queue, and C doesn't see anything else. Next in the queue is D. Now D does see E because E is not yet in the queue. So D does see E, so E is added to the queue. And well, how much flow have we got to D? We've only got 1 flow. We've only got 1 unit to D because it came not from B but from A. So we can only get 1. Well, anyway, we've only got a spare capacity of 1, so that matches up. So we can get a flow of 1 from D to E. So E can get 1 from D in the forward direction. Now we're almost finished. What is next in the queue? Next in the queue, we've done D. Should have ticked these off. We did C, we've done D. Next in the queue is F. Not E, but F. So F, we can get to T. So T is labelled. T is added to the queue. And we can get 1 unit. We've only got, well, we got 2 units to F actually, but we can only push 1 of those to T because the spare capacity here is only 1. So since although we had two at T, sorry, 2 at F, 2 flow we managed to get to F, we can only get 1 of those to T. So T is labelled with 1 on it. Now that's finished our pass, if you like, our sort of forward pass across the network. So what is the conclusion? The conclusion for this iteration is that our augmentation number is 1. We can get an extra flow of 1. It's a bit disappointing, but that's the way it is. An extra flow of 1 to the sink. And I'm now going to follow that through, and you'll see it's come all the way from the source. How has it come from the source? Well, to do that, we start at T. Now T has come 1 unit from F. Okay, that's what I just said. But where did it come from F? It came from C. So although it's only 1 unit, we could have got 2 to F, but going backwards, we've only got 1. So the 1 came from, we can make the 1 come from C. And what happened at C, from C, it came from A, and from A, of course, it came from S. So that's our, that's our augmenting path or winning path. Okay, so now we update the flow numbers. We put new flow numbers we change the flow numbers because we can get 1 unit more, and we use certain edges to do that. So instead of a flow of 3 from F to T, it's now a flow of 4. That means this edge is now saturated. Instead of a flow of 2, this becomes a flow of 3. Instead of a flow of 3, this becomes a flow of 4. And instead of a flow of 2, this becomes a 3. So we've updated those numbers. We don't change the other numbers, okay? But we now start again and do a new iteration with those numbers. Okay, I'll try and remember the path because I'm now going to move on and put it again on the. So we forget everything we did before apart from the new flow numbers. So let me just put the new flow numbers on that. So there was a flow of 3 here. There was a flow of 4 here, a flow of 3 here, a flow of 4 here, which means this edge now is saturated, as was this already, and that's it. So we now have to start again and do a second iteration. Let me try and do this a bit more quickly. So some of it's just going to be the same. So we start from S. Again, it's a good idea to have the Q. We start from S. We can still see both A and B because neither of these edges at the start are saturated. But we can only get one. We can only get 1 unit to A this time. We can still get 2 units to B. The stuff at the bottom hasn't changed much. Excuse me. So then we move on to looking at A in the Q. A we can still get to C. We've still got our net flow from D. That deals with A. Then we look at B, which is next in our queue. Nothing has changed much here either. We can't see C because that's already been dealt with, and we can't do D because that's already been dealt with. So nothing to do at B, because there was nothing before. And then we go on to C. Now again, we can still see F from C, but there's only one spare capacitive 1 only this time. That does C. So let me just circle the vertices that have been seen, so to speak. Sorry, Q. So we've done C, and now I look at D. So D we can see E, and there's a spare capacitive 1 to get to E. Now you see F. Although F is in the Q, it can't see any vertex because this path to T is saturated. So we then pass to E this time, and we can see T from E, but we've only got 1 unit to E, so we can only get 1 unit to T from E. So again, epsilon, it's now the second epsilon, is again equal to 1, and it's coming from E. So what is our winning path? We've got the 1 unit from, it's not the colour I wanted, we've got the 1 unit from E, And how did it get to E? It came from D. How did it get to D? It came from A in the backwards sense, and from A to A it came from S. So let's just look a bit more carefully about what's happened there. Let's update the flow numbers first of all. So with this second iteration, the flow numbers, what are they? The 4 becomes a 5. The 1 here, what have we done? We've reduced it to 0 because this is a backwards. You see the path, the winning path, so to speak, was started at S, it went to A, it came back from D. The arrow's going like this. It went forward from D to E. So I just realised I made a mistake there what I said. And then it went to T. So you only, what do? You add epsilon to the forward path. So this 1 becomes a 2. But because this is a backward path, this 1 becomes a 0. You subtract epsilon because this is a minus path. And this 3 becomes a 4. So this edge is now saturated. And you see that the fact that this is reduced here to 0 means that we've diverted the flow because it was 3 plus 1 is equal to 4. This time it's the 4 is going straight ahead to C, which is fine. So we've diverted flow. Remember, we always have to have conservation of flow at each vertex. That's the point. So the 4 now is becoming 2 plus 2, this 4, because there's no leakage here anymore. This 4 has become 2 plus 2, so that's fine. And everything is working out. Okay, so we've now, what did we do? We started with a flow of 2 plus 5, which was 7. The value of the new flow now is 4 plus 5. Don't confuse the flow numbers with the capacitors. You can look either at S or at T. The new value, the value of the new flow after 2 iterations is equal to 9. So we've now got a flow of 9 from the source to the sink. Now what happens if we try and go on? Now, do I remember these numbers? I'm not sure. Let's see if I can label with the new flow numbers. We had 4 here because this is now at capacity. We'd made this 0. We'd made this at 2, which makes this edge at capacitor, which I forgot to say. This 4 had become 5. This 3 had become a 4 in the first iteration, so this was already at capacity. We had 4 went on to a 4 here. This was already at capacity. The 2 and the 4. So we had 2 and a 4 is 6. 2 plus 4, I'm looking at the flow numbers, 2 plus 4 is 6, this 2 had to be a 3, this became a 3 rather. We had a 3 and a 1 that went to a 4, so I think that's now correct. So that's the current flow situation. The value, as I say, is equal to 9. Now we can try a third iteration. What happens, and I'm not going to go through the details, but what happens is you can start. So when you start the queue, A is no longer in the queue because this edge is saturated, but you get B in the queue. And you can start labeling B can see both C and D because there are forward edges with spare capacity. So we can get both B and D. And then we look at C. C can still see F. and it can even see, let's see, it can see F, C, sorry, we'd already seen C. A, it can also be seen from C. But we can't actually get any further. We can't find spare capacity or non-zero flow coming in to do any more labeling. And this actually defines, because of what I said in the previous video, this defines a minimum cut for this network. Okay, so what we do is we take these vertices which we've added, which we've got to in the third iteration, the vertices being A, well S of course we started at, B, C, the ones which we could label in the third iteration, everything apart from the E and T. So this gives us a cut in which all the vertices on the left-hand side and E and T are on the right-hand side. What is the capacity of this cut? Well, for the capacities, we forget the flow numbers. We just look at the capacities on arcs going forward across the cut. And the capacities are 3 plus 2 plus 4. Okay, that's 9. Okay, so the capacity of this cut, of this green cut, is 9. And that tells us that we can't have any more flow. We've got a maximum flow. Remember, after 2 iterations, the flow value is 9. It's the sum of these numbers, 4 and 5. Not the capacities, but the flow numbers. The value of the flow after 2 iterations was 9. The value of any flow is less than or equal to the capacity of any cut. If those two numbers are equal, the flow is maximum and the cut is minimum. So this is a minimum cut in which we just have 2 vertices as capital T. This is a minimum cut in which capital S is these green vertices and capital T is little e and the sink T. So that's how you can use the labeling algorithm to find both a maximum flow and, if you continue for one more step, one more iteration and get as far as you can, a minimum cut. You could have probably spotted this minimum cut in advance, but if not, that's how you can get it. Okay, that's the essence of the labeling algorithm for flows.